Okay, we're going. So 2 problems here, I just want to make sure that we know how to do. Very common type of problem to show up in a Calculus 1 course. One of these showed up as a bonus problem on the last quiz, or something very similar. I think I probably changed the numbers here, but something something similar to this one showed up on the last quiz. But it's a very common type of question to ask. You'll definitely see a problem like this on the first exam and the final, pretty much. So I want to make sure that you guys know how to solve these. And so let's actually get through these. A. Okay, so here we have a function. Now, when I say we want the function to be continuous, so exactly what do I mean? What does it mean for a function to be continuous?
Yeah. No discontinuity, like no holes, no gaps.
No discontinuities. In other words, it should be continuous on the entire domain of the function. What is the domain of this function, as described?
X less than 0.
Huh?
X less than 0.
I didn't. What did you say?
For the 2 signal X less than 0.
No. If I ask you about this function, f of x here, and I ask you what is the domain of this function, what would you say? Yeah.
All real numbers.
It's all real numbers, right? It literally covers everyone. There's a part of it that works for if x is less than 0. There's a part of it that works for x equals 0. There's a part of it that works for x greater than 0. So in other words, the input values that we can plug into this function covers everything. Okay? So when I say I want this to be continuous, I'm talking about it must be continuous on the entire real line, no matter what x value I plug in at any point, it needs to work. So the domain is all real numbers. I want you to make it continuous on all real numbers. The issue here is that there are letters here, A and B, that are meant to represent constants that you should be able to solve for. X is the variable. And I want you to choose constants so that this will actually be continuous on the entire real line. There will be no holes, no gaps, no breaks, no anything like that. Okay? So hopefully now we understand the issue. Now how do we go about solving such a problem? So what's the first thing you want to do here? Ideas. Want to figure out where it's continuous, where it's not continuous, maybe fix it. What's your first thought? What do you think? Yeah?
You have to make you have to make sure that the equations, when like transferring from one equation to the other, like line up kind of, like they equal the same thing, like at the transition, or they approach the same thing.
Oh, like at the transition points, like when you're transitioning from less than to equal to 0, we need to make sure the functions connect, basically, right? Okay. There's one thing that I would consider before that is, it's probably a hidden problem, but it is something you should worry about, is let's say not even worrying about the connection points. Each function individually, where would they work, right? So what about this one, sine x over x? Where is that continuous? Yeah? Everywhere except 0. So this guy works when x is not 0. We don't have to worry about that because we're told that x is not 0. So we're only applying this when it's less than 0. So even though that fails at 0, it is okay for us. It's fine. What about 3a? What kind of function is that? Where is that continuous? Yeah? Everywhere, because that's just a constant. That's just a number. So this one would work for all real numbers, right? Minus infinity to infinity. So again, individually, this is fine. What about this one? Yeah?
Also everywhere?
Also everywhere. Because cosine is defined everywhere, and we're just multiplying it by a constant. So this works everywhere. So individually, everyone is fine. So now we realize that the only thing we have to worry about is where they actually connect. Where do we transition from one definition to the other? We need to make sure that at that point it's behaving. So we can start out by saying, if x is not 0, we're fine. Right? 0 is where things break into 3, right? So at 0, at the specific point it takes on this value, immediately to the left and right it takes on other values. Individually these functions are fine where they are, but we want to make sure that at 0 everyone is connected, right? So if x is not 0, we're fine, so what we need to now do is check at x equals 0, what's going on, right? So we want to make the function continuous. What do we need to make sure happens in order for the function to be continuous? Yeah?
That each piece connects to the others, to the ones that. So the first piece connects to the second piece connects to the third.
Yes, that's true, but that's like the answer in English. What is a mathematical way? What is a mathematical criteria? Yeah.
The limit as x approaches a of f of x has to equal f of a.
Right, which in this case is 0 specifically. We want the limit as x approaches 0 of the function to be equal to the value of the function at 0. So when I ask you to make something continuous, you need to make sure that that equation is satisfied. That's what it means to be continuous. Yes, we know the intuitive meaning, but we want something, the mathematical meaning, something we can actually calculate, right? So it's not like, oh, we're kind of guessing, does this connect? No, we know specifically the criteria that we need to fulfill. That's the equation that defines continuity at point. So if we're not at 0, everything's cool. So now at 0, we need to force things to work. In other words, we need to force them to fit this definition. Now you'll realize that this breaks into 3 parts. There's a part that tells you what's going on to the left of 0, and this is different than what's going on to the right of 0. So that automatically tells you this limit you have to think of into 2 pieces, right? We need to worry about what is going on at the left. We also need to worry about what's going on the right. Right? So we really have to consider the 2 one-sided limits here. Right? And we need to make sure that literally everyone, the limit as we approach from the left of 0, the limit as we approach from the right of 0, and the value of the function at 0, these all need to be equal. They all need to give you the same value. Right? So those are the 2 things starting out that you should realize. 1, make sure each piece works individually on whatever domain it's defined. 2, and as long as that's fine, you need to identify the points where the function breaks into different definitions, and you need to make sure that at these transition points everyone is connecting. What does it mean for them to connect? This equation holds. Okay. So let's start by looking at f of 0. What is f of 0 in this case? Yeah.
3a.
It's 3a. So remember, a is a constant, it's always going to be the same number. When x is 0, that means we're looking at the middle function, 3a is going to be that. Okay. Now let's consider the limit as we're approaching 0 from the left of x. This means I'm taking the limit as x approaches 0 from the left of what function? Who's the function I'm considering? Yeah? The top one, right? Coming from the left means I'm coming from this side, which means on the number line I'd be less than 0. So this is for what our function definition is to the left of 0. So on this limit I will be taking the limit of this particular function. And what is that? It is 2. Because we know the limit is x approaches 0, sine x over x is 1. Okay, so now we need to check, what about coming to 0 from the right? This means I should be taking the limit of what function? The bottom one, right? 0 from the right means I'm coming from this side, means I'm getting close to 0, but I'm slightly bigger than 0 at the same time. This guy tells me what's happening when x is bigger than 0, so that's the function that would apply here. Now what's that limit? 4d, correct? So in other words, what do we need to have continuity? We need all these numbers to be the same. We need 3a must be equal to 2, must be equal to 4b. Or in other words, you can split this into 2 parts. We need 3a equals 2, and we need 2 equals 4b. So this implies, what do we need? A should be 2/3, and B should be 1/2. And those values will make this function continuous. Choosing these values will make all these three definitions, they will connect at the transition points. And they will all connect at the y value 2. Right? So the thing that was messing up here, we actually had a hole at that for the y equals 2 and x equals 0. But choosing a and b to be those values, we fixed the problem. We removed the discontinuity. I think in the quiz I gave you slightly nicer numbers. These were supposed to be like whole numbers, but in this case, you know, if it's a fraction, it shouldn't be too much different. So again, you have a problem like this. You want to make a function continuous. Check each definition individually because they might have their own problems. As long as you're satisfied that they don't have their own problems. But it might be the case that they do have their own problems, and you can either fix it or not. To fix it, you can either add something to the definition, or if it can't be fixed, just say it can't be fixed, and there's no choice of A and B that will make it continuous. But as long as they're all working, now you only have to worry about the transition points, where when we switch from one definition to another, do these two actually connect to the same point? How do you know when things connect? Well, you don't have to draw the graph or anything like that. You just simply need to check an equation. Check that at that point, the limit approaching the point is equal to the value of the function at that point, and graphically they will connect. There will be no break, no gap, no holes, no nothing. That tells us it's continuous. So oftentimes with piecewise function, you need to consider the one-sided limits because you'd be depending on what side you're coming from. But ultimately, you just need to make sure that this as a whole works out. And here, you can, once you know that, the rest of the problem should be easy. It's kind of following your nose. You're just plugging in the value, taking the limits. At this point, you should be super good at taking limits, and then you can end up finding values. Let's look at the second example. Are there any questions on this one? What would you consider here? What would you look for? Yeah?
We need to find a domain for each.
Okay, what's this guy? Where does he work? Yeah?
Everywhere.
Everywhere. It's a polynomial. What about this guy? Also everywhere. He's also a polynomial. This guy. Where does that work? Yeah?
Above -0.5.
Above and at negative
Yeah.
0.5 can be greater than, you need 2x plus 1 to be greater than or equal to 0. So you can be minus a half or anything bigger, and that guy's going to work. So now, obviously this guy might have a slight issue. Is it an issue for us? No, because we don't care about some point beyond negative a half. We're at 4, right? So this is fine, and this, it has some issues, but they are of no concern to us because we're far away from that issue. So that's also fine. So individually, these all work out. So now I need to make sure that they, at the transition points, they all connect. So what are the transition points here? Yeah?
1 and 4.
1 and 4. So we know that if x is not 1 and x is not 4, we're fine. So now we have to check each of those. So let's start by checking x equals 1. How do we ensure that things work out at 1? What do we need here? What do we need to happen here to get things to work out at 1?
Finding the values in the
No. As an idea, what's your goal? Yeah?
The limit approaching 1 of x minus 1 squared.
Limited. We start out with just writing down the definition. You need to know where you're heading, right? I need to make sure this works out. Okay. So. Right, sometimes the students don't know where they're heading. Sometimes they don't know, should I stop or do I keep going, right? You need to know where you're heading. That's the goal for now. I need to make sure that that equation works. Now, once you decide this is what I need to make sure it happens, you can talk about specifics. How do I make sure that that happens? And again, there's a section for when x is less than 1. There's a section for when x is greater than or equal to 1. So we are going to have to consider 2 limits here. We need the limit as we approach 1 from the left. We also need to talk about the limit as we approach 1 from the right. So let's deal with 1. F of 1 is what? Yes?
A plus B.
A plus B. Right? F of 1 means we need to look at the part of the definition that applies when x equals 1. That's the middle one. Here it says x is greater than or equal to 1. We want to be equal to 1, so I'm looking at this function. When x is 1, this function is a plus b because I plug in x equals 1. So that is f of 1. So now let's talk about the limit as we approach 1 from the left of f of x. What limit am I looking at now? Yeah.
X minus 1 squared.
Top one. Limit as x approaches 1 from the left means we're on the left of 1 coming up, which means we're less than 1. Top function deals with that. So that's what we have to figure out. And what's that? Yeah, 0. And so now let's talk about going to the right of 1. And what's that? The function we should be looking at is the middle function, ax plus b. Right? Do not look at the bottom function. Right? Why? Because remember, a limit talks about getting super close to 1. This guy is for bigger than 4. 4 is super far away from 1. Right? This is the guy that gets super close to 1. Right? Because it deals with x at 1 and slightly bigger, moving all the way up to 4. So you should be looking at the middle one, not this one. 4 is too far away from 1. This one gets arbitrarily close to 1, so that's still the function. And again, a plus b is going to be the answer. And so now, in order to be continuous at 1, what do we need? What do we need to work happen here? Yeah.
A plus B has to equal 0.
A plus b must be 0. Now, we have to find a and b. Can I find a and b? Not exactly, right? I have one equation, 2 unknowns. This is not enough information. So at this point, you wouldn't freak out. You'll just remember there were 2 points that I have to check. Hopefully by checking the other point, I'll get some more information that can be useful. So I would just run right into checking x equals 4. As always, we know what we need here is the limit as we approach 4 of f of x must be equal to f of 4. So now I go through and I start to check all these conditions. What is f of 4? Yeah.
Root 5.
Huh?
Square root 5.
Where?
Sorry, 4a plus b. I was looking at the bottom equation, but
Yeah.
it's the middle equation.
Yeah, it's the middle equation because here it can be equal to 4. So that is 4a plus b. Right? What about the limit as we approach 4 from the left? What function are we looking at? Huh? 4 from the left.
The same.
What's in function?
A plus B.
X plus b. 4 from the left means we're less than 4 coming up. So we need to see where is x less than 4. It applies here. It's the middle function. So that's also going to give us 4a plus b. Not really giving us any new information there, but we still have another side to check. So let's see. If you approach 4 from the right side of f of x, what am I looking at now? The bottom function. That tells you what's happening when we're greater than 4. So I'm taking the limit of this function. And what's that?
3.
That's 3. So ultimately, to make it work at 4, what do we need?
4 plus b is 3.
We need that 4a plus b must be equal to 3. Can we find a and b? Yeah.
Yeah, so you have to set a equal to, or no, you have to set b is equal to negative a, and then you plug in negative a to b in the last equation for it.
Right. So you can solve for one here, plug it into there, so you get this equation, one variable, which you can solve for that variable, and then backtrack. That's called solving a system of equations by substitution. I don't particularly care how you do this. You should just know how to solve something like that. It's, going back to algebra class. So you realize now what you have is that you have a plus b equals 0 and 4a plus b must equal to 3. These conditions must be satisfied simultaneously, so you have a simultaneous system of equations. Multitude of ways to solve these. I'm going to use elimination because if I look at equation 2 minus equation 1, 4a minus a, you get 3a, b minus b, you get 0, 3 minus 0, you get 3, so you get a equals 1, which immediately implies that b is minus 1. So that's the solution. So, among other reasons, of course, limits are important for their own reasons, but among other reasons, a lot of times on the quizzes, you notice that I gave you several limits. I gave you 6, I think, on the last quiz, right? Because I want you guys to be very good at computing limit after limit after limit, back to back, just knocking them off rapid fire, because there are problems where in a single problem, you have to be taking a bunch of limits coming from different sides. You shouldn't be getting confused, and you shouldn't be spending too much time doing this. You need to understand what is the overall goal that you need to achieve from the problem. You need to know how to get there. And in this case, to get there, we needed to take 4 limits, 4 one-sided limits. And you shouldn't be slowed down at all by this, because by this point, you should be so good at limits, it's like, you can just say what they are by looking at them. Because every now and then it comes up that a single problem will have, you have to find a bunch of limits in that one problem. Yeah. Here. But yeah, like I said, this is a very typical kind of problem to show up in a Calculus 1 class. So definitely know how to do these, as well as just knowing how to find limits in general. On your first test, there'll definitely be a problem like this. There will also definitely be a problem where it's just one problem with several parts for you to find several limits. That's going to be a question for sure. And you have to use various techniques there. Okay, so now that we have our brain juices flowing, let's get into some definitions and terminologies that I want you guys to make sure. So last time we saw, well, I don't believe I gave you this definition. I'll tell you now. Definition. If f of x is not continuous at x equals a, we say f is discontinuous there. So the opposite of continuous is discontinuous. Just telling you what preposition we use. You don't say uncontinuous or non-continuous. Discontinuous is usually what we call it. We also saw that every now and then a function can have a discontinuity, but we can fix the discontinuity by redefining the function at the specific point where it's messed up. This usually happens if your discontinuity is a whole. And so last time we ended the class there, so let me remind you of what that is. sometimes f can be redefined a finite number of points. To remove its discontinuities. Discontinuities that can be removed in this way are called removable. Last time we saw examples of removable discontinuities. So for example, the function y equals sine x over x was discontinuous at x equals 0, but you could actually fix that function. You could develop another function that in spirit, it's just like sine x over x. It behaves exactly like sine x over x, except for one point where sine x over x misbehaves, we can create a new function that behaves. And so if we ever want to deal with sine x over x, but we don't want to have to worry about its discontinuity, we could just use the other function, and then everything will be fine. Right? Not all functions are that nice though. Some functions you can't fix them without drastically changing the definition and the behavior of the function. And functions that exhibit that kind of discontinuity are said to have essential discontinuities. F has a discontinuity that cannot be removed is called an essential discontinuity. There are two main types. There's the jump discontinuity. That means when your function does something like it's behaving one way and then it jumps up and behaves another way. Right? It just makes a little leap. Probably of some finite height. That's called a jump discontinuity. These guys are non-removable. Why? Because to actually get these two sides to connect, you literally have to move an entire half. You literally have to fix an infinite number of points, an uncountably infinite number of points. You will literally change the essence of the function in order to fix that point, that function at 0. It can't be done by moving a finite number of points. Yes? Okay. Right? You literally have to move an infinite number of things to fix that. And it's less than countable infinity. Now, there's also the infinite discontinuities. So that's kind of the discontinuity exhibited by something like 1 over x squared at 0. Right? So it makes kind of like an infinite jump from one side to the other. You're right, you can't just describe the jump by a finite distance. And so again, to get these two guys to connect, it's impossible to do that by just moving, hey, just redefine this point here. You can't do it. Right? To get this to connect, you have to literally change how the function behaves pretty much entirely. You lose the essence of the function. So those guys have what we call essential discontinuities. So continuity is important to the point where whenever it can be fixed, we want to fix it because it will make things a lot nicer. However, there are cases where it can't be fixed, and these are called essential discontinuities. And at least in calculus of the real variables, these guys are super hard to deal with. If you're doing complex analysis, then you can actually get some nice results out of those as well. Yeah?
You're not predefined asymptote?
No. Like, how would you redefine that? Like, if you had y equals 1 over x squared, if x is not 0, what would you put here that's going to fix it? 5? No, that's like you just filling in here. 7? It's like you filling in here. X plus 1, that would still be just a point, right? You can't bridge that gap without essentially changing the function. It wouldn't behave like 1 over x squared anymore. You definitely can't do it by just moving a single point, or a few points, or 10 or 20 or 1,000 points. You need to remove like an entire branch of the function to get that to behave. So we have removal discontinuities. We saw an example of that last time. There are also essential discontinuities. There are a couple of examples of essentials. What else do I want to talk about? One-sided continuity, maybe. Let's talk about that. Just like you have one-sided limits, there's a concept of having one-sided continuity. This just means it's like the continuity equation, except you use a one-sided limit in the definition. So we say f is continuous. Just give me a definition. From the right, at x equals a, if the limit as x approaches a from the right of f of x equals f of a, that's called continuity from the right. So it's kind of like the continuity definition, except you only look at one side of the limit. Similarly, and approach a from the left side of f of x, and it's equal to f of a, we say it's continuous from the left. Why would we need a concept like this? Because sometimes we want to be able to call a function continuous, even though it will not fill the original definition of continuity. And it's not because we want to cheat, it's just because there are some things from an intuitive perspective, it should be continuous. It's a picture that doesn't have a hole, doesn't have a gap, doesn't have any break, but yet it cannot fulfill the definition that we had before. A very simple function that we like working with here is the square root of x would fulfill that definition. Now intuitively you want to say that's continuous. There's no hole or break in that function, but at 0, what happens? There is no left of 0 when it comes to the square root of x, right? There's only a right side, right? But again, we want to be able to say square root of x is continuous. There's no craziness going on. It's just that to the left of 0, it doesn't exist, right? So in other words, we would want to have a definition that would include square root of x in our list of continuous functions without having to break the definition, and so we define these two continuities. So when it comes to the square root of x, we only consider the continuity coming from the right side of 0 if we're at the point 0, and with that we'd say it's a continuous function. So in that sense, we also need another definition. F is said to be continuous on an interval I if it is continuous for all points in I. If I includes its endpoints, then we consider one-sided continuity. So with this, we can see now, for example, we can say y equals the square root of x is continuous, right? Because this function exists at 0, moves to the right. Now, if we want to take the limit at 0, the thing is you need a left side and a right side. However, it is continuous on this interval. It includes its endpoint 0. So it means at that point, we only worry about the right side continuity. We just ignore the left sided continuity because we want to be able to call this continuous. And to that end, let me tell you which functions we shall consider in this class to be continuous. So pretty much all the functions that we'll work with in a Calculus 1 class have a very nice behavior. They are continuous on their domains. So of course, I mean on their domains here. So there are a list of functions that are continuous. They don't have breaks or gaps or jumps or holes or anything like that. That we know once we're dealing with these functions, we don't have to worry about such issues. These are polynomials. Polynomials, their domain is all real numbers, but they're also continuous on all real numbers. Any point on the number line you decide to set up that continuity equation, it will work out. Polynomials are continuous on their entire domain. Based on the definition I gave you here, radicals are also continuous on their entire domain. Rational functions are continuous on their entire domain. You might recall a rational function is just a ratio of polynomials. So like 1 minus x squared divided by 3x cubed minus 7x plus 1. That's a rational function. As long as the denominator is not 0, such a function is continuous. Exponential functions, which we covered at the beginning of this class, are continuous on their domain. So are logarithmic functions. What are the functions I want to say? Polynomials, radicals, rationals, exponentials, log, trig functions. Sine, cosine, tangent, cotangent, cosecant, secant. These functions are all continuous on their domain. Parentheses here, algebraic functions. We'll talk about this next time. An algebraic function for us will simply be some combination of several of these functions via the arithmetic rules and composition. So if I take a polynomial times a radical, or a rational divided by an exponential, or something like that, if I use some sort of mathematical operation to combine the previous 6, I create what's called an algebraic function, and these are also continuous on their domain. Combinations of continuous functions yield continuous functions. And these are pretty much all the functions we'll look at with Calc 1. Turns out that all the functions we like to study, they are continuous. Which is it's very nice. I want you to appreciate, to wrap up here, yes, and I will wrap up here. I want you to appreciate that this is not a trivial consideration or a trivial statement. Some of you might think, well, why wouldn't a function be continuous on its domain? If we're on the domain, that means if we plug in that value, it's going to work. Why wouldn't the function be continuous at some points where it works? Well, here are some examples. I'll give you a very simple one to start out. Here's a function . Right? Let's look at that function. Right? That's this guy. I wrote an example of that earlier. What's the domain of this function? Yeah? The domain is all real numbers. This is a function the inputs will work no matter where you are. I can plug in any number on the real line, it will give me a meaningful value. However, as you can see, it is not continuous. At 0, it breaks. So just because you can plug in anything doesn't mean you have to be continuous. So the domain is all real numbers, but it is not continuous on all real numbers. It is discontinuous at x equals 0. And in fact, it has an essential discontinuity. It's a discontinuity you can't fix. Yeah.
Doesn't this also hold true for rational functions? Because if we have a denominator which shall be equal to 0.
Then such a point is not in the domain, and it wouldn't be considered in the first place. When we talk about continuous, we say continuous on their domain is the definition. As long as you can plug in a number, the continuity equation will work for that number. Another nice function, we're not going to see a lot of it, but it's a very popular function. Floor function, for example. This is a function that rounds down. So you give me a number and it just cuts off the decimal point. Right? So if I tell you 2.1, this will output 2. 3.7, this will output 3. 14.9, this will output 14. It's called the floor function. It always rounds down. It is also defined for all real numbers. Here's what its graph looks like. These are also called step functions. There's the floor function and there's the ceiling function, a function that always rounds up. But as you can see, the domain here is again all real numbers. But notice that it has an infinite number of discontinuous points that are essential discontinuities. So for me to say these functions are special because they're continuous on their domains, it's not a trivial thing. Most functions are not this nice. Most functions are crazy and they behave like this. And they are very problematic for us in calculus. Most of our times will be spent with the nice functions. These functions, once I can plug in a number, it will be continuous at that number. And this will be very useful for us. It will make our lives a lot easier. We'll end there, talk a little bit more about continuity next time, and then move on to verbs. See you guys on Tuesday.
Technically, yes.